Well, it seems to have become the tradition for me to open these conferences by talking about my kind of evolving view of the data universe. And it's each year there are new and different things that happen. For me, these are very exciting times because there's a technology stack that we've basically been building for close to 30 years that is really coming together beautifully, and many things that we've been working towards for decades now are sort of just finally coming to fruition. It's kind of a mixture of things we've done and things that have happened in the world that make this possible. Obviously, the technology we've built has been widely used in research and development for many years. I mean, 90% of universities in the US now have site licenses for our technology, and it's used throughout sort of the research and development world. I think the thing that is particularly exciting now is that we've really cracked how to put all of the stuff that we've built into production in very kind of industrial environments, so to speak. And I think what's to me exciting about this is it really changes the sort of the character and economics of what's possible with sophisticated computation. And it seems like this is the year when this is all finally happening. It's a mixture of lots of engineering that we've done, lots of building up of our technology stack, lots of things that have happened in the world in general. You can kind of tell that something interesting is happening because there are all sorts of Silicon Valley startups that are starting to notice that, gosh, you can use our technology stack to do all kinds of things that never been possible before. That's usually a leading indicator of other things going on. I mean, we've actually been holding back a bit on really announcing, promoting everything that we have, because we've been doing lots of difficult engineering to really consumerize being able to scale up the kinds of capabilities that we have, and especially in things related to the cloud. And it's almost done. I think within months, I think we will finally be at the point where we feel completely confident that we've built something that is scalable all the way. I mean, we've done a number of tests. You may have noticed during this year a few things. I'll probably talk about them a bit later. Kind of interesting websites that have shown up, that a couple of them that got to 1 million users in their first day. Part of the reason we did those was because we thought they were interesting websites, but part was because we were testing the scaling of our infrastructure to make sure that it will actually work up to those kinds of scales. And the good news is it does actually work. So the thing that has been sort of a theme of everything we've tried to do is sort of automate everything, kind of automate as much as possible in the way that computation gets done. And now the new thing is also automating the deployment of computation, making kind of the machine do as much as possible, and the humans just have to sort of define the goals and then let the machine figure out how to achieve those. Well, let's see if we can go here. Yes, good. So kind of the one mode of that is the whole Wolfram Alpha experience, where the goal has been to kind of have a zero learning environment where you can just ask questions in natural language, and where Wolfram Alpha will figure out sort of what are some things that you might find interesting to sort of generate an automated report that shows you not just the specific answer to your question, but also related things that it thinks you might find interesting. And this kind of zero learning approach to being able to ask questions and compute knowledge-based results has been very successful. It's used in lots of places, sort of consumer places like Siri and so on. It's also used every day by many millions of people directly on the web, and it's become sort of a dominant thing in how students, for example, find information in areas like math and science and so on. So, but the things that we're really sort of Wolfram Alpha is kind of the zero learning kind of approach to dealing with a very wide range of knowledge, and we've covered a lot of different areas. That we've been trying to make use of data and knowledge and set it up so that any question which can in principle be answered on the basis of systematic knowledge that exists in the world, we can automatically answer when the question is given to us in natural language. But the thing that has sort of the centerpiece of the technology stack that we've been building for such a long time and going forward is what we call the Wolfram language. And the Wolfram language is sort of a merger of the technology that's emerged from our Mathematica system and Wolfram Alpha and lots of new things, and then also now feeding back into Mathematica and Wolfram Alpha and so on. But sort of the centerpiece of all of this is Wolfram language. And kind of the idea of Wolfram language is it's a knowledge-based language. It's a language where we try and build in as much knowledge about computation and about the world as possible. Kind of the traditional approach to computer languages has tended to have a rather small language, and then perhaps people build libraries to do specific things on top of that small language. What we've done with the Wolfram language now over the course of nearly 30 years is to build something where we try and put as much knowledge right into the language as possible. So it's a very big language, as opposed to being a small language. It's a big language with 5,000 sort of built-in primitives and so on. And the goal is to have a coherently designed system that covers a very broad area of capability. Well, so I think we've used the Wolfram language to do many things. For example, Wolfram Alpha is written in the Wolfram language. It's about 15 million lines of Wolfram language code at this point. The Wolfram language kind of spans very small code to very large code. It's also been the place where we've taken a lot of data that we've accumulated, for example, for Wolfram Alpha, in making data sort of accessible in Wolfram Alpha. We've had to get to quite a high bar of making the data computable, in the sense that if there's a question that can in principle be answered on the basis of that data, we should make it sort of automatic to be able to answer that question. The bar is still higher when we're integrating that kind of data into our sort of systematic Wolfram language environment. And so one of the things that we've been doing is taking a lot of data, including some from people here, and getting it to the point where it's computable to the level that it can be used systematically in the Wolfram language. Well, so there are lots and lots of things that can be built with the Wolfram language, and we're starting to see all sorts of things in the world built with it. But maybe I should start off and just sort of show you a few things that we can do, and both sort of traditional things that one's been able to see for years, and also, of course, lots of new stuff, because that's the fun of running a software company, is you get to show all the new stuff that doesn't really exist yet, which means it probably won't work properly, but we'll see what happens. So things are alive, it's working. Let's see what we can do to. I'll just do some sort of live coding kinds of things to try and give some kind of feeling for what it's like to do things in the Wolfram language. So, like for example, we might have some function, Roman numeral. Okay, so we get some Roman numeral. Let's say we make a table of Roman numerals from, let's say, I don't know, up to 100, let's say. Okay, so there's a bunch of Roman numerals. Let's say let's do some sort of really elementary data science. Let's say we make a list line plot of string length let's just take this and use that. Let's say like this. Okay, so there's the sort of the efficiency or inefficiency of Roman numerals as let's go up to 200 or something. It's kind of an interesting pattern. We could, for example, say let's use a different plot theme here. Let's go. I don't know. Let's do a marketing-oriented plot theme here. Okay. So it gives us some kind of visualization of our Roman numerals as a function of size. Or for example, we could say let's take something like this, and let's say let's make a histogram of those lengths. Okay, there we go. Maybe let's do it up to 1,000 here. Okay, that's kind of interesting. Surprising the source for a potential Gaussian. I don't know. Now I'm really curious whether now I got to find out. We've got we have a nice function here. Let's see what it does. Okay. Oh, it says it's a binomial distribution. Okay, with parameter 0.4. So that was again, it's a pretty automated thing we're doing here. We've just got some data, and we're now just saying find distribution, and it's looking in the sort of space of all possible kind of name distributions to try and find the one that fits best in this case. I don't know. Let's try doing something like let's try something slightly different here. Let's take our Roman numerals. Let's take a few fewer Roman numerals, and let's say. How about we do this? Let's make a graph. Let's make a nearest neighbor graph where we're using, I guess, some kind of edit distance to know the distance between sort of neighboring things. Okay, so here we've got a graph that shows kind of how the Roman numerals, what Roman numeral is nearest in some edit distance to what other Roman numeral. So we can make all kinds of graphs. I don't know. We could pick up this graph and we could make let's say we make a community graph plot out of that graph. So we can just use this graph, put that graph into that function, and now we're getting, I don't quite know what this means, but we're getting sort of the clumps of Roman numeralism. I'm not quite sure what that is, but I have to think a little bit more about it. So okay, so this is so that was some sort of something fun. Let's try something different. Let's pick up an image, for example, here. Let's see. Okay, let's do it again. Okay, there we go. There's an image. So now we could, for example, say, let's try making. Let's try just saying something like partition that image. So let's take the image here, and let's partition it into little things of size 20 or something. So now we've got that image. We could go ahead and we could say, sort the rows here. And maybe we could assemble that image into something. It's kind of weird. We could, if we wanted to, we could. Let's take this and let's say, for example, let's just do a different kind of analysis. Let's say we make a 3D chromaticity plot, which is going to give us the color levels in that image. Okay, so there we go. And now maybe what we can do is we can say, let's make a dynamic, I don't know if this is going to work, but let's see. Let's make a dynamic chromaticity plot of the current image. So what we're going to, that's going to be showing the color levels let's see if this works. Okay, and now probably if I start waving at it, it's not so obvious what it's doing, but that's giving me now the sort of the real-time display of the chromaticity of that image. Maybe I can pair that. I could do something simpler. Let's just say, and we can do some very standard thing, like let's just to prove it's doing something sensible. There we go. So now it's edge detecting me in real time. So again, we can do all sorts of things with all sorts of different kinds of data in the Wolfram language. Let's pick up some other. Let's try getting some data. Let's just try pulling in something from the outside world. Let's say we pull in the, if it wakes up, let's see. Come on. I hope we're connected to the network. If we're not connected to the network, it's going to be bad. That's really odd. I think we're connected to the network, otherwise I wouldn't have been able to reach various websites here. Okay. That's not what I expected at all. Anybody from our team got any ideas what's going on? No? All right, let's try something here. Let's do some real-time debugging. Let's try that. Humph. First of all, it shouldn't need to be updating, and second of all, if it is updating, it should be updating quickly. Well, that's a shame. I thought I was going to be able to do some nice thing, pulling in data from Wikipedia. All right, let's see whether we can see whether this is a bad sign. This is a very bad sign. Okay. Well, all right, we will be able to do something here. All right, let's try this. Okay, so let's get like an English dictionary, and let's say, how about we do this? Let's take take the first letter from 100,000 words in an English dictionary, and then let's say something like, let's make a word cloud out of those. So this should be, okay, so this is showing us a word cloud of what the most popular first letters are in an English dictionary. We could maybe do the same thing, I don't know, let's do the same, we could do that for, let's say we do it for a Russian dictionary instead. Then we'll get a bunch of other letters here. We could do the same kind of thing again, unless this is not accessing the network, which it probably needs to do for this. Hump. All right, let's try something here. Let me just see whether things are even vaguely alive, or whether the network is just, no, that's working. Okay, that's odd. Very odd. How about, well, okay. We'll keep going, hope for the best. Okay, so one of the things that's sort of interesting about Wolfram language is it's kind of mixing things that are happening locally with things that are happening in the cloud or being retrieved from the cloud. And normally, it's all perfectly seamless, and you wouldn't know that there were two different places where computation was happening, except when you can't reach one of them. So another big thing about Wolfram language is the knowledge that it has of sort of real-world data. So, for instance, assuming this is going to work, we could type in something like Washington, D.C. Okay, oh, there we go. That did work for some reason. So what happens is we're using, in this case, natural language to kind of specify all these different kinds of entities in the world, and now we have this thing that is an object that we can manipulate in our language, just like any other kind of thing, just like an image, just like a graph, just like a string or something, but now it's a real-world entity. And there are tens of millions of these real-world entities that the system knows about. So, for example, I could say, I don't know, something like, let's say US states. Okay, so there's US states, and now let's get a list of those entities. Okay, there's a list of US states. And now, for example, let's say I could say, let's try doing something like entity list of that, comma, flag. So this is going to hopefully give us the, that's interesting. I didn't mean entity list, I meant it turned red, which is good, because that's showed me I did something wrong. Okay, so let's say I want to get, I'm going to ask about the flags of all the US states. Okay, so there are a bunch of state flags, and now I could, for example, ask for, I don't know, I could say, how about I do this? Let's say, I could say something like, show me the dominant colors of all those state flags. Or I could go and say, let's take, okay, so there's the dominant colors from those flags. So now, for example, I could do something, I don't know, let's say I could take, I could create a function that represents, that computes what's nearest to a given thing. So, for example, here I have this nearest function, and I could say, take that nearest function and take a US flag and tell me the states, let's say the 5 state flags that are nearest, according in some measure of nearness. And I don't think any of them are particularly close to the US flag. Those are the ones that it thinks by some measure of visual similarity. It's really odd that it thinks that one is, but that it thinks are near to the US flag in some such measure. So let's try. How about we try something different? Let's try. And again, we're making. Let's just. Oh yeah, it's kind of fun to see if we did something like. Let's do this. Let's take the state flags and let's find the populations of all the states. So let's say. What was that? I should have given names to these things, but I didn't. Okay, so that's on line 8. So let's say I ask for those, and I say what's the population of each of those, and so they'll give me the populations of all the states, and now I say take that and the actual state flags. There we go, line 9, and let's make an image collage of those state flags, where the weighting in the image collage is proportional to population. So that's showing the state flags of the US in a size weighted by their population. It's kind of cool that we can do this in sort of 1 or 2 lines of code and so on, and with data that's all built into the system. Okay, then I'll actually learn some state flags from this. We could certainly do that. Well, let's see, what will we do? We've got our dominant colors here. How would we do this? We would have to say, I think this requires a little bit too much thought. We could plot the dominant color as a function of, we could do a scatter plot of the dominant color as a function of population. Let's not do that because we'll end up getting, I will have a very bad habit of doing these experiments, doing deeper and deeper experiments live. Let's try, okay, how about, let's take our US states, for example, and let's do something different here. Let's say we take the US states and let's say, how about we do the capitals? So again, we're going to use this will now use natural language to give us to let us do the queries. So there's a bunch of results of the capitals. Let's go ahead and get let's go ahead and find out what the geo positions of all those capitals is, and then what we're going to do is take those geo positions and let's say we can say find a shortest tour. Solve the traveling salesman problem. Okay, wake up, computer. What are you doing here? Come on. Why it's something as odd is going on, because some things that should be super fast are taking forever. Probably, yes. So you never know what happens. That's the oh dear. I'll tell you what. Let's just try saying this. Let's just try doing. Let's try. See if this works. Okay, well there we've got a bunch of, so those are the geo positions of the state capitals. Now we can say find shortest tour of those. So this will now give us the ordering. So it says the 16,000 miles is the length of the tour. And now let's take that second part of that and let's apply it to line 17. Let's do this. So this should give us that sequence of positions for the state capitals. And now let's say, let's make a geo list plot of that with joined true. So we want to join them all up. And now what we should have here, let's see whether this works, is come on. This should give us a nice picture. Something very odd is happening here. Okay, let me just see whether things are working at all. Let's see if it knows where we are. Okay, so there's the geo position that it thinks this computer is at. So let's say we make graphics, let's say of a geodisk around here with radius of, I don't know, 5 miles or something. Let's see whether this works. Aha, it thinks we're in the middle of nowhere. Okay. It thinks we're in Kansas, okay. Well, we have to tell it we're not in Kansas anymore. And that's also very odd, okay. Okay, yeah, that's the 1,000-mile diameter version of that. Okay, so let's just try this one more time here, because I think it would be cool to see this. Oh, there we go. Okay, it worked now. So that solved the traveling salesman problem for a tour between all U.S. state capitals. So again, I think it's pretty nice that we have state-of-the-art algorithms for solving the traveling salesman problem, and it's all kind of freely accessible because you just type find shortest tour and it figures out the right way to solve the traveling salesman problem for that number of items and so on. In this case, on the surface of the Earth, so it understands. You can see that line is slightly curved there because in this projection, that's what's happening and so on. So it's just easy to figure out lots of stuff. I don't know, you can, it's nice to explore different kinds of data. So for instance, let's say we've got something like, let's see if I can do this, something like geo-elevation data for the Earth. So here I'm just going to, let me just get sort of the complete geo-elevation data for some grid on the Earth. And now I could say, for example, make a histogram of all of those values from geo-elevation. So this tells us for sort of everywhere on the Earth, this is the histogram of what the height of the surface is. So it's kind of interesting, actually. I made this plot a couple of months ago for the first time, and I was sort of surprised. There's lots of land that's right near sea level, and then there's this weird peak down at I guess this is in feet, so at like 15,000 feet below sea level. So I thought that was sort of interesting. But it's kind of nice that you can just take. We have all this geo-elevation data. We have actually very detailed geo-elevation data for the Earth, and you can just pick it all up and make that plot and find something interesting about it. So we've been steadily accumulating data on lots of kinds of things. I don't know if we say something like, how about we do this? Let's take a random. Let's just go for a particular domain. Let's say a random entity. Let's say 30 random movies. Okay. And now we could say something like get, for example, images associated with 30 random movies. Okay, we weren't lucky that time. Let's try it again. Let's try another 30. What am I doing? Okay, we have of all possible movies, we have posters for the vast majority of them. So I don't know why Okay, that wasn't very exciting. Only a few movie posters there. But in any case, we could, if I'd said, give me a bunch of random movies. Let's get 100 random movies. Let's try and get posters for them. I could have tried to do an analysis of, I don't know, let's say how the dominant colors of these posters have changed over the course of time. Let's say if we delete the missing ones here. I don't know what those missing ones may be from very small budget movies that aren't too exciting. But we can go and do our dominant colors thing here, or we could go and compute sort of images as a function of time and so on. Lots of kinds of things we can do. We could go ahead and we could say, I don't know, we could say something. We could use some natural language here. We could say movies by, let's say, directed by. Steven Spielberg here, and hopefully we'll understand that natural language. Now let's get a list of those entities, and we should get a list of entities, and we can then get posters for those and go on and compute all kinds of things. So we, as I say, we've been collecting data on sort of every possible thing. The bar for having this data be computable is very high when you can actually do things directly in the Wolfram language with it. An example, something we've recently worked on is anatomical data. So, for example, if I say, let's say skull here, and let's say we have about 80,000 objects in the human body. So, for example, if I say skull and I want 3D graphics, let's see if this works, I should be able to get high-resolution 3D graphics with actually the whole kind of, okay, there we go. And there it is in proper 3D. Or let's take something a little bit smaller. Let's take a femur, for example, and actually what I probably want to say. Come on, wake up, computer. Let's just say left femur, for example, and then let's say something like let's get the mesh region of the left femur, and so that will now give me a something where I could actually start computing. I could do finite element analysis on this thing or whatever I want to do. Or I could just say, let's just do something simple. Let's just say, what's the area of that? And that will give me the area in I think, square millimeters here. So there's sort of an inexorable process that we've been going through, trying to add data on everything. And we've developed a lot of, I think, quite interesting expertise over the last decade in sort of how to curate data and make it computable. It's a hard business, and it requires one of the things that's kind of difficult about it is it requires judgment calls at kind of every turn. It's not something where you just, shovel the data into a computer and expect it to do everything for you. It's something that actually requires human experts to be injected into the process to really make something that's useful and working. And we've been, as I say, we've been adding all kinds of areas. An area we recently have added a lot of stuff for is cars. Let me show you an example of that. Let's say something like, let's go to Wolfram Alpha. Let's say compact cars with the largest, say ground clearance. See what it does. So hopefully, come on, connect. What is wrong with this network? Arg. Wake up, connect. Okay. See whether it can figure that out. Well, something is very amiss here with how this is connecting to the network. Come on. It's frustrating when I think the actual come on, computer. Okay, well anyway. This is what I get for doing live demo. Let's see whether anything works here. No, our generic Wi-Fi, so I don't know what's happening. Well, anyway, it would be nice if we, okay, for some reason now it works. Okay, so this is giving us, I have no idea if this is correct, but I'm sure it is. This is giving us for 2015 cars that are EPA classified as compact passenger cars. This is giving us some ranking. And I'm sure if we press one of these, we'll see a lot more detail about that particular kind of car. This is just one domain. This happens to be a quite complicated domain because there are lots of kind of variations, and the ontology is pretty elaborate. But we can get here's some data on pricing. Here's some data on fuel economy and so on. Lots of kinds of things that we can compute about cars. Okay, this is the Wikipedia page hits history for that particular kind of car, which tells us something about sort of the level of interest and public visibility that it's had as a function of time. So anyway, we've been doing over the course of the last many years, we've been adding more and more built-in data to the public Wolfram Alpha that people use every day. Another thing that's been happening is we've been building a whole bunch of custom Wolfram Alphas for large organizations. And that's been a very interesting and successful business. Lots of custom Wolfram Alphas have been built that have curated data from within organizations. And actually this year we'll see the first few of those that happen to be also getting exposed to the outside world for various kinds of consumer purposes. So that will be an interesting thing, making use of our natural language understanding stack and mixing typically curated data from within an organization with kind of public curated data that exists within the Wolfram Alpha knowledge base. So, in any case, there's a lot of data that is built into Wolfram Alpha. One of the things that we've also been interested in is dealing with sort of the flow of additional data in real time from devices and so on. Obviously, we have lots of real-time feeds that tell us about earthquakes and market prices and weather and all kinds of other things. But the question is, can we easily take some connected device that's been produced and flow data from that into our cloud and into our technology stack? And one of the things we've been interested in, we've been sort of curating. We curate all kinds of things. We've been curating kinds of connected devices. Here's the website where we have data on a couple of thousand kinds of connected devices that measure all sorts of different kinds of things. And you can say what kinds of things they measure. They measure all sorts of things. A typical interaction with companies that make these kinds of devices is they built some great device. They say, we've got this sensor, it measures really well. Say, what are you actually going to do with the data from this sensor? They say, well, we're going to hire a bunch of programmers and build some cloud backend to feed data from our sensor into. And so one of our goals has been to have them not try to do that, because it's really hard and there's no point in everybody doing it for themselves. And so we've been trying to build a sort of general cloud backend for connected devices and sensor data and so on. And that's been rather successful, and a whole bunch of companies are starting to use us to provide the sort of cloud backend for data that comes from sensors. So let me show you what happens. I should show you so the thing we built is, we call it Wolfram Data Drop, and the idea is that it's a place where you can just drop data somehow from things through an API. You can tweet to it, you can use an Arduino, you can use various other kinds of devices. One recent thing, I wonder whether it's listed here, is being able to use if this then that. You can use all sorts of different methods to get your data from a connected device into the cloud. Once it comes into the cloud, it will come in as a data bin. So for example, I could go and look at what data bins do I currently have. Okay, so there's a bunch of sensors that I have sitting on my desk. Let's say I take that the data that has been accumulated from the little board of sensors that I have sitting on my desk at home, and this should give me. Let's see if this works here. This should show me the data that's come from those sensors. Okay, there we go. So here's some data: humidity, light, pressure, temperature. Okay, let's take this. Let's get a time series of that data, and let's have to wait for this whole thing again. Okay, so now let's take for example, the pressure time series here, and now, for example, I can do the date list plot thing on that again, and I'll get that's pressure as a function of time for the sensor on my desk. It's kind of fun to take a look. Let's take a look for line 44. Let's say let's find out what the first date there was. Okay, let's get the last date in that time series. And now let me go ahead and say air pressure data for Concord, Massachusetts, which is where I live. And let's say that from that first date, line 46, to the last date, line 47. And let's try to retrieve from public data the air pressure between those two dates. And let's then say, let's get ready with the date list plot here. Hopefully, come on, wake up. Hopefully this will be able to get the air pressure data. It's kind of weird, actually, all these oscillations that you see here. I wonder what that's due to. Maybe that's daily. No, I'm not sure. Okay, we should be able to find out. I don't know what's happening. Oh, dear. Okay. With luck, this will go and give us some air pressure as a function of time. One of the things that we're working on, so the data drop is this place where you can just take data from some device, for example, or from some process that's going on, whether it's people filling out a survey or lots of other kinds of things, and just throw this data into a data drop. Each data drop gets some unique ID that we can then is then accessible either from the web or from inside the Wolfram language or from other languages, and you can then go and do computations with the data from that data drop. There we go. We finally got it. Okay. So this is now, that was the public data for that. That's the time series for. So they look actually rather similar. Let's take a look here. Let's say. Okay, so this is that's comparing the data from my desk with the data from local weather station, and there's probably an overall difference because the altitude of my house is a little different from the altitude of the nearest weather station. But it gives you some idea of how one can get data from a little real-time device and compare it with public data and so on. So in any case, the data drop is this way of getting sort of feeds of data from little devices Another thing that we have been building is what we call our data repository, which is intended to be more a place for people to put large blobs of data. And the idea is to have an easy way to get access to those large blobs of data from within the Wolfram language, and to set it up as a place where, for example, people who are doing research can, publish their data, which is something that everybody's sort of wanted to see happen, but it's been a thing that's been hard to achieve in a way where the data is actually usable. One of the really important things about data in our kind of ecosystem is that it's sort of immediately computable and meaningful. We have this thing we call WDF, Wolfram Data Framework, which is kind of an exposure of the ontology that we've built, a sort of algorithmic ontology that we've built for Wolfram Alpha to allow people to take their data and put it in this kind of standardized computable form. So, for instance, even at the very simple level, data comes with, quantities come with different kinds of units. Okay, there are 10,000 different kinds of units that are in use, all of which we have sort of carefully curated for Wolfram Alpha, and all of which are now sort of immediately accessible within WDF. So let's see. Maybe one example. Let me try one example of what you can do with that. Let's see if I have this. Yes, I do. Okay, so here's an example. Here's a recent example of using sort of our sort of ontology on food. And this is a slightly more elaborate example. Let me just make it bigger. So this is just looking at different kinds of foods, and you can say, I don't know, there's a egg whole fried cooked food item, and here's things that we know about it, like its nutrition label and all sorts of other detailed quantities of amounts of various different kinds of things. Here's an example where we're looking at a kind of implicitly defined entity, where we say it's a food type entity, its approximate shape is a sphere, its typical outside color is red. Now let's get an image of it, and so now we're getting red spherical kinds of foods. And being able to do this kind of thing within our sort of algorithmic ontology, I think is an interesting and important thing. Well, okay, so and that's something that's made possible by this WDF mechanism. The other thing to understand is that because we've also got our natural language understanding stack, we can take things that come from sort of unwashed spreadsheets and so on, and understand that yes, this column is a place name, this column is a date, and so on. And the way that works internally, we have this whole mechanism of what we call interpreters. So, for example, there are hundreds of different kinds of these. If I say, something like the Eiffel Tower here, and I say interpret that as a location, this will now give me the geo position of the Eiffel Tower. Okay, so let's take a look at some other kinds of things. So one question is, when you get data into our language, what are some convenient ways to kind of handle that data? So one thing that we've recently introduced is something which is kind of our version of a mixture of kind of SQL and NoSQL database technology, kind of made into something more unified and modern by the fact that our language is a symbolic language. I should have mentioned that the fact that it's possible to have a thing in the language, which is an image or a graph or a representation of Washington, D.C. or a movie or something like that, is made possible by the fact that this is a symbolic language. So so any one of these kinds of things, if I say something like this is just a symbolic object that the system can recognize, can deal with as a symbolic thing. It doesn't have to have a value of 17 or something. It's just a symbolic object that the system is dealing with. So here I've got, here I had something where I'm looking at, I'm asking, I'm saying, get me, this is just an example data set that's kind of a mixture of something kind of tabular and something hierarchical. I could go ahead and I could say, planets, all, radius, for example, and that will give me the radii of planets. I could say, make me a bar chart of this. I could say something like, let's say I want some planets, and I want all planets, and I want the moons of the planets, and then I want to take the total mass of all the moons of each planet. So this is now going to take me in this kind of data set. This is now going to give me the what it's asking for here. So for example, if I just said something like this, I could say something like, give me the length of the number of moons listed in this data set here. Or for example, I could say something like, how about I try saying, all right, let's try doing this. Let's say, instead of saying all here, let me say select the length of hash moons. Okay, so let's say, what I'm going to do here is I'm going to say, give me all planets with, give me only the total mass only for those planets that have more than 10 moons. So this is how we would do that kind of query. And I could say, I could then, if I wanted to, I could say pie chart of that, chart legends. I want to say something like that. So that will then give me a pie chart of that, and so on. Okay. Well, and we can do all kinds of other computations like this. What's interesting is the way that we get to use kind of symbolic language combined as part of the sort of querying mechanism for this kind of symbolic representation of a data set. Okay, well, lots and lots of other kinds of things we can do. Maybe I should talk now about how one takes these kinds of internal computational capabilities and deploys them to the outside world. So for example, how would we sort of deploy an app to the outside world? So let's say we make some trivial thing here. Let's say we make something that just plots, makes a plot here. Okay, great. And now we have a little slider to control that plot. Now let's say we want to deploy this to the outside world. Well, what we can go ahead and do is to say cloud deploy this thing, and now we'll get something which has deployed that manipulate to our cloud. Oh, come on. And if I sign in, I should be able to see this. Okay, that's a little weird. So this will now show me, apart from that weird glitch, which I very much don't understand. This is what I get for running yesterday's version of our language. But in any case, the point is this is a pure web page, and I just took the thing that I created on the desktop within Wolfram Language, and I deployed it to the cloud. So now I've got this little cloud app that does that. Or for example, I could say, let me take something like, how about I do this? Let's say I want, let's just say position of the ISS. Okay, so this should give me position of and let's say, let's make a geovisible region of that. And let's make a geographics of that. Oops. And now, okay, so this should show me, oh great, it's over the ocean. Let's try doing this. Okay, there we go. Okay, so it's in the middle of the Pacific Ocean. I could do another geo projection to make it prettier, but let's try and make an app that shows the position of the ISS. So what I want to do is I want to say make this delayed, so it's only going to be computed at the time when this is when I ask for it. And let's say let's make this a publicly accessible app. And now what I'm going to do is it will now deploy that to the cloud. Now whenever I go to that cloud location, it will, oh, I forgot to do something here. It will give me, it should be able to say, I want to put it on the web, so I want to say export it as, for example, PNG. Okay, so now I will have created a little app that whenever I go to it, it will show me the current position of the ISS. If I wanted to, I could now pick up that app. Let's see, that app should be visible. Actually, let me do this. Let me say, I'm gonna make this app accessible elsewhere. Let's do this. Okay, so now let's say, I go to my phone, and I go and I look at the Wolfram Cloud app on my phone. Let's see if we can see this. And someplace here should be the thing that I just deployed, hopefully. Where is it? Always, I should have deployed it. How about I deploy it to an actual named thing? That way I'll know where it is. Let's call it ISS. Okay. So now hopefully we will see here. Unless I'm logged into a different server or something confusing. No, there we go. There's the ISS app that we just made. So I can now go to it on my phone, and I'll get that same result. Or if I wanted to, I could go and deploy this app to my watch, and I could go. Let's see, we get next level in the stack. Let me not do this. I just have to tell it here to make that available on the watch. There we go. Select objects to go on your Apple Watch. There we go. Save that. And now I could pull that same app up on my watch, and it will compute the same thing. So okay. So that's a little bit more on how you can kind of deploy an app. Let's try something where we want to make. Let's see if this works again.